Today we're going to learn a little more about where exactly electrons are located in atoms. So far we know that the electrons are found outside of the nucleus somewhere. They're not just anywhere outside the nucleus, they're somewhere in particular, and we're going to learn how to identify where they are. To do that though, we need to first understand the properties of light. So it's light that led to the discovery of where electrons are in an atom. So let's start with this. Light has wave-like characteristics. Let's draw a standing wave on this line. So something like that. Some properties of waves. Amplitude of the three properties is the least important. Amplitude has to do with the height of the wave. Not significant for what we're going to do. Another property of waves are something called wavelength. The symbol that we use to represent wavelength is a Greek letter lambda. So it kind of looks like an upside down Y. Now, wavelength refers to the distance from corresponding points on two consecutive waves. So the distance from the top of one wave to the top of the next, or the bottom of one wave to the bottom of the next. So that distance there would be wavelength. When we're talking about wavelength of light, this is usually given to us in nanometers or angstroms. A nanometer, if you recall, is a billionth of a meter, so 10 to the negative 9th meters. Angstrom is 10 to the negative 10th meters. I think your book primarily uses nanometers. And another property of a wave is called frequency. The symbol for frequency, again, is a Greek letter, nu. Kind of looks like a V. Frequency refers to the number of waves that pass a given point per second. So think about waves at the beach, how many waves hit the shore each second. That is known as frequency. Frequency of light is measured in hertz, symbol is Hz. A hertz is the same thing as a per second. So notice we have seconds to the negative 1, also called a per second. Go ahead and open your books to page 182. There's a figure I want you to look at. Pause the video if you need to do this. So in that figure at the top of the page is something called the electromagnetic spectrum. And what this shows is the different types of electromagnetic radiation or light. Sometimes they're just referred to as light. I don't like to call them all light. I'll refer to them as electromagnetic radiation. So all the way on the left we have gamma rays, and then X-rays, UV, visible light, infrared, microwaves, all the way to long radio waves on the right. So those are all the different types of light or electromagnetic radiation. Now, if you look at the top scale, the scale at the top is frequency in hertz. So we have gamma rays, 10 to the 24th. We have long radio waves, 10 to the 0 hertz. So we see that frequency is increasing right to left across the electromagnetic spectrum, at least the one shown in your book. If you look at the bottom scale is wavelength in angstroms. I misspoke there. It's not given to you in nanometers, given in angstroms. Again, 10 to the negative 10th meters. So for gamma rays, we see wavelength of 10 to the negative 6th angstroms. And then long radio waves, we see 10 to the 18th angstroms. So what do you notice about the scale for frequency and wavelength? Well, wavelength increases from left to right, and frequency increases from right to left. So what this tells us is that frequency and wavelength are inversely related. As a quantity of one goes up, the other goes down. Mathematically, how do we show that two variables are inversely related? Mathematically, we would see that the product of two variables that are inversely related is equal to a constant, and that's what we have here. So here is the equation showing the inverse relationship between wavelength and frequency. C equals lambda nu. So again, in our equation here, lambda is the wavelength in meters. probably not going to be given to you in meters, so you need to convert it to meters. Nu is frequency. That'll be in per seconds. And then C is a constant, the speed of light. The speed of light in a vacuum is 300 million meters per second. We'll go 3 sig figs, 3.0010 times 10 to the 8th meters per second. Now going back to the electromagnetic spectrum, notice that visible light makes up a really small part of all different types of light. Make sure you know the colors of visible light. I'm going to put these in order that's different than your book. So usually the electromagnetic spectrum is written the other way around, where wavelength is decreasing and frequency is increasing. So the colors of visible light, Roy G. Boeuf, there's no indigo there. Red, orange, yellow, green, blue, and violet. So some important things about the colors of visible light. Red has the longest wavelength. Violet has the shortest. Red has the lowest frequency. Violet has the highest frequency. Notice too in your book it shows that energy increases from right to left. So what we see here is that the lowest energy light is red, has the lowest frequency and lowest energy. So this means that red light has a smaller frequency and a longer wavelength than orange, yellow, green, blue, and violet, or violet. All right, let's take a look at an example. Read along with me, please. Example 5.4 on page 183. Light near the middle of the ultraviolet region of the electromagnetic radiation spectrum has a frequency of 2.73 times 10 to the 16th per second, or hertz. Yellow light near the middle of the visible region of the spectrum has a frequency of 5.26 times 10 to the 14th hertz. Calculate the wavelength that corresponds to each of these two frequencies. So I'm not going to set this up for you now. This is well, you know what? Let's set this up. Let's do one of them. So let's do the electromagnetic radiation. We have a frequency of 2.73 times 10 to the 16th. We want to calculate wavelength. So let's take our equation and rearrange it. So we're going to take the speed of light divided by the frequency, and that'll give us the wavelength. Let's do that. (2.73 times 10 to the 16th). Go ahead and pause the video, punch it up on your calculator, make sure you get the correct answer. You should get this number. And then if we were asked to, in this case, we want to find the wavelength in angstroms. And so what we'll do is we'll take that value and we'll multiply it by 10 to the 10th. So there are 10 to the 10th angstroms per 1 meter. And that'll give us an answer of about 110 angstroms. And the book does not show that. I'm not sure why. I think there's a typo there. 110, 1.1 times 10 to the second angstroms. If we want to convert that to nanometers, the wavelength from meters to nanometers, we would multiply by 10 to the 9th. There are 1 billion nanometers in a meter. All right, try one on your own. Go ahead and do number 39 on page 212. I don't know if it specifies wavelength in nanometers or angstroms. So let's take a look there and make sure. It says to calculate it in meters. So let's do this. Let's calculate in meters, nanometers, and angstroms. And let's just go ahead and do letter A. I don't think we need to do more than that. So number 39A, page 212. Go ahead and pause the video. So here are our answers. If you want more practice, go ahead and do B and C, and you can ask me for those answers later. Next up is a relationship between energy and light, the different energies of light. We saw in the electromagnetic spectrum that energy increases from right to left. We see that frequency also increases from right to left. So what that tells us is that the frequency of light and energy are directly related. So again, let's write a mathematical equation showing the direct relationship between energy and frequency. It looks like this. We have E equals h nu, where E is the energy in joules. This is technically joules per every 1 photon. A photon's a tricky thing. It's just a bundle of energy, a packet of energy sometimes it's called. So 1 photon, that's what we're calculating for E, the energy per every 1 photon. H is a constant known as Planck's constant. Need to memorize this value, or it's probably given to you on your equation sheet. 6.63 times 10 to the negative 34th joules times seconds. Nu is our frequency again in hertz or per seconds. All right, take a look on page 183. This time we're going to calculate the energy of those photons of light in the example at the top of the page. So we took the frequency, we calculated the wavelength. Now we're going to take that frequency and use it to calculate energy. So let me just show you how that is set up. So we're just going to take Planck's constant, multiply it by the frequency. Make sure to put in per seconds and not hertz. The seconds will cancel. We're left with joules. Again, that's joules per 1 photon. We get 1.81 times 10 to the negative 17th joules per every 1 photon. Sometimes you're asked to find the energy per mole of photons. So let me show you how to do that. So here's what our setup looks like. Any guesses how many photons there are in a mole of photons? A mole of anything is the same amount. Sometimes we're asked to find the energy in kilojoules per mole. So in this case, we just take our answer we would get here, convert the joules to kilojoules. So go ahead and practice on your own. Number 41 on page 212. And again, we'll just do letter A. We did 39A. Go ahead and do 41A. Calculate the energy in joules per photon as well as kilojoules per mole of photons. Pause the video, please. Hopefully you got this. If not, we'll discuss it in class. So it's a pretty large amount of energy, about 2,000 kilojoules per mole, which is quite a bit of energy. Let's take a look at a little different problem, 5.6 on page 185. Read along with me. A green line of wavelength 4.86 times 10 to the negative 7th meters, which happens to be 486 nanometers, by the way, is observed in the emission spectrum of hydrogen. Calculate the energy of 1 photon of this green light. So before, when we calculated energy, we used the frequency to get energy. Here we're given wavelength. So we have 2 choices. You can do this in 2 steps where you take the take the wavelength and use that to find the frequency. And then once you have the frequency, you can calculate energy. Or we can substitute. Let's take a look at our 2 equations we have. What if we substitute in our first equation for nu? And we'd end up with an equation like that. So you can go directly from wavelength to energy. Just combine those 2 equations. And so that's what's being shown in example 5.6. Make sure again that your wavelength is in meters. Speed of light is going to be meters per second. Planck's constant joules seconds. So everything's going to cancel except for joules. And again, as it shows in the book there, that is the energy per photon. And they show as well the energy per mole of photons as well. So once you give one of those a try, number 45 on page 213, which just happens to be a green triangle. Don't be scared. You can do it. So what's going on here, just to walk you through it, plants absorb light. They absorb light of a certain wavelength, and then they transmit or emit is what it says there. They give off light of a different wavelength. So what we want to do is calculate the energy of both of those lights. So the light that has 440 nanometers wavelength and the light that has a wavelength of 670. And then the difference is what the plant uses for photosynthesis. So again, find energy for each of those photons. The difference will be the energy that the plant uses. And we're going to find that energy in, I think we can do joules or kilojoules per mole. We don't want to do just a single photon, so we'll do it per mole. All right, pause the video and work on that. All right, so the light that has a wavelength of 440 nanometers has an energy of 4.52 times 10 to the negative 17th joules. That's per one photon. The light with a frequency of 670 nanometers, 2.97 times 10 to the negative 19th joules per photon. Again, the difference between the energy that's absorbed or taken in by the plant and the energy that's given off is the energy that the plant uses for photosynthesis. 1.55 times 10 to the negative 19 joules per photon. I didn't put per photon there, but that's per photon. Take that back. We want those moles still there. And we end up with 93.3 kilojoules of energy per mole of light that the plant then can use for photosynthesis. So we still haven't gotten to the relationship between lights and the location of electrons. We're getting there. All right, next up, quantized light energy. So let's do this. I'm going to draw a couple things here. It says in the notes, steps of a ladder. Let's draw a Bohr model. So we have the nucleus at the center. The electrons orbit around the nucleus in these things called energy levels. So what was shown in, especially with the emission spectrum of hydrogen, only certain colors of light were given off. If you look on page 186, towards the bottom of the page, it shows different emission spectrum. They're called line emission spectrum. So these are the colors of light given off by excited atoms. We'll talk about what that means in a little bit. So take a look at hydrogen. So excited hydrogen atoms only give off light of certain colors. We have violet, blue, green, and red. Remember, the different colors of light correspond to a different amount of energy. So what that tells us is that the electrons possess a certain amount of energy. The electrons exist at only certain distances from the nucleus in these things called energy levels. So again, it's kind of like steps of a ladder as well. So a little lesson on potential energy. Objects that are attracted to each other, that are separated by a distance, have potential energy, which we can calculate using mgh. M is the mass, g is a constant, h is distance from attracting bodies. So let's say you step up on the first step of the ladder. Well, you're so far from the ground, you possess a certain amount of energy. Go to the next higher step. Well, now you're further from the ground. You're further from what you're attracted to. Your energy increases. The further you go up the ladder, the higher you go up on the ladder, the further you are from the ground, the higher your energy. Same thing goes with electrons and atoms. They are attracted to the nucleus. So the electrons, as they get further and further from the nucleus, possess more and more energy. Notice that the energy levels, the distance between them is not the same. There's a good picture in your book, page 187, and it shows this, that as you increase in energy level, the distance between the energy levels decreases. And so again, the point here is that the electrons can exist only certain distances from the nucleus. If the electrons could exist at any distance from the nucleus, you wouldn't see what you see on page 186. you would get something known as a continuous spectrum, not a line spectrum. All the colors of light given off. That's not the case. Electrons can only be certain distances from the nucleus. Likewise, you can only be certain distances from the ground when you're on a ladder. You can't stand between two of the steps. Electrons can't exist between two of the energy levels. They're either this far or this far or this far or so on from the nucleus. Certain distances and then certain colors of light are given off. Some more evidence showing the quantized nature of electrons is the photoelectric effect. Take light, shine it on an atom, and it'll cause electrons to be expelled. So if you add energy to atoms, you can remove their electrons. And again, it takes a certain amount of energy, and then the electrons have a certain amount of energy associated with them, and then the difference in energy is what's registered on the meter. So, a little better than the last lesson. Last lesson, we said the electrons are found somewhere outside of the nucleus, orbiting the nucleus. Now, they're not just outside the nucleus, they are at specific distances from the nucleus in these things called energy levels. So when I say the term energy level, what you must think is distance from the nucleus. First energy level is closest to the nucleus. Second energy level is a little further. Third energy level a little further, and so on. Again, going back to our Bohr model, and the model shown on page 187, figure 517 there at the bottom. Again, we can see different energy levels and how the distance between them decreases as the energy level increases. Some vocabulary terms, ground state atoms. This refers to a situation where an atom has its electron, if it's hydrogen, just one electron, or electrons in the lowest energy position possible. All the electrons are in the lowest energy position possible. We call this atom in the ground state. If an atom has one or more electrons in a higher energy position than in the ground state, it is known as an excited atom or excited state atom. This occurs when atoms receive an input of energy. So we can cause atoms to become excited by giving them energy in the form of heat or electricity. For example, a blacksmith uses heat to bend metal. When they put the metal in the fire or the metal glows. It's because those iron atoms are excited. Here's the important part, very, very important, number 3. Why does it glow? Well, it glows, light is given off when electrons move from a state of higher energy to a state of lower energy. So it takes energy to bump electrons up to a higher energy level. When electrons go from higher energy level to lower energy level, energy is given off in the form of light. And again, as we saw with the line emission spectrum for hydrogen, only light of certain wavelengths is given off. Certain wavelengths, certain amount of energy, which tells us then that the electrons are quantized. They possess only a certain amount of energy. All right, one more piece to our puzzle here. Electrons exhibit both wave-like behavior and particle behavior. So the de Broglie equation shows the relationship between wavelength and velocity. Here's the equation. We're not going to spend too much time with this equation. It's plug and chug for the most part. Again, just know that there's a relationship between wavelength and velocity. So there are the variables. So what this implies is that all objects with mass have a wavelength when they're moving. There's some examples on page 191 and 192. Go ahead and take a look there. It says calculate the wavelength in meters of an electron traveling at 1.24 times 10 to the 7th meters per second. Gives you the mass of the electron. We have Planck's constant. We can use that to find wavelength. And then we have a similar problem. This time we're using a baseball. Again, we can plug those values in. Take a look in the middle of that page. It shows a nice relationship in terms of what to do with the units. A joule is a kilogram meter squared per second squared. Let me write that out for you. Without knowing that, the units don't work out. So we have joules, and so we need to plug in kilogram meter squared per second squared in place of joules in Planck's constants units. And that way kilograms will cancel, so mass has to be in kilograms. Meters per second, that's a unit of velocity, so meter squared per second squared is velocity squared. And so meters per second will cancel. The seconds will cancel, and Planck's constant will be left with just 1 meters, and that is our unit of wavelength. Go ahead and do number 63 on page 214. Go ahead and pause the video, and I'll give you the answer. So we end up with a value that is 1.68 times 10 to the negative 10th meters. I went ahead and expressed that also in angstroms, 1.68 angstroms. All right, next time we'll get even a little better in terms of describing where electrons are in atoms. Thanks for watching.